Module 1, Lecture C, Types and Input. By the end of this lecture, you will be able to distinguish between strings, integers, floats, and booleans in engineering calculation contexts. Build interactive scripts that accept user input and convert it to usable numeric values, and format calculation results clearly for engineering interpretation and reporting. Core data types. Floating point values. Floating point numbers let Python work with decimal values used in engineering, such as measurements and voltages. Because floats can be used directly in calculations like scaling and unit conversion, they are essential for accurate measurements and simulations. Choosing floats when decimal precision is needed helps programs behave as expected. Floating point numbers let computers represent very small and very large values by shifting the decimal point as needed. Because they are stored in binary, many decimal values can only be approximated, so small rounding errors can occur. This is usually acceptable in engineering work, but extra decimal places from sensor data or unit conversions should not be mistaken for greater accuracy. In engineering, floating point numbers should match measurements that can vary continuously, such as temperature or speed, and they are useful when calculations produce decimal results. They should be treated as practical approximations, not exact values. Engineers also need to consider significant figures and rounding, since computers may show more digits than the measurement actually supports. Python code, floating point values. Floats are used to represent measurements that include decimal values, which are common in engineering calculations involving fractional quantities. Proper formatting helps present these results with realistic engineering precision. Floating point values are used to store precise measurements with decimals. In this example, the beam length is 2.75 meters, the voltage is 3.3 volts, and the pressure is 101.325 kilopascals, preserving the precision needed for engineering calculations. The code checks the data type of each engineering value, including beam length, voltage, and pressure. It uses the type function and reads the type's name to confirm that each value is a floating point number. This helps ensure the precision needed for engineering calculations. A bolt diameter is first set to 0.375 inches, then converted to millimeters by multiplying by 25.4. The result gives the same bolt size in metric units. A total load of 1,250 newtons is shared equally among 3 supports. Dividing the load by the number of supports gives the load carried by each support, with a precise floating point result. Adding 0.1 and 0.2 with floating point numbers can produce a result that is slightly off from the exact decimal value. This happens because some decimals cannot be represented perfectly in binary, causing small rounding errors. These differences are usually tiny, but they matter when high precision is required. The example shows how formatting makes numerical results clearer in engineering reports. A bolt diameter is rounded to 2 decimal places, and the load per support is rounded to 1 decimal place. It also shows that adding 0.1 and 0.2 can reveal small floating point rounding errors, which can be hidden by formatting the result to 1 decimal place. This script shows how floating point numbers are used in engineering calculations, such as storing measurements, converting units, and dividing loads across supports. It also demonstrates that floating point arithmetic can introduce small rounding effects, as seen when adding 0.1 and 0.2. The final outputs are formatted to appropriate decimal places, emphasizing the need for clear precision when reporting engineering values. Integer values. Integers are whole numbers used when values must be counted exactly, such as bolts or sensors. In engineering and programming, they show that the data represents a count or index rather than a measured quantity with fractions. Using integers clearly helps prevent confusion and supports accurate communication and calculations. Integers are essential in engineering computations because they represent exact counts and positions. They are used for indexing measurements, numbering simulation steps, and counting optimization iterations, while decimal-based quantities use floating point values. Keeping these roles separate makes the meaning of each value clearer and helps improve calculation reliability. A number's type affects how a program interprets it. An integer is different from the same digits stored as text or as a decimal, even if they look similar. In engineering, this distinction helps separate labels from counts and measurements, such as treating a pump ID as text, but the number of pumps as an integer. Choosing integers when values are meant to be counted helps prevent errors and makes calculations clearer. Python code. Integer values. Integers are used to represent engineering quantities that are counted. This distinction matters because counts are different from labels and measurements, even when these data types may seem related. The number of bolts and sensors is stored as integer values, 12 bolts and 4 sensors. Integers are appropriate because these are discrete counted components and they support accurate, straightforward arithmetic in engineering calculations. Use floating point numbers to store engineering measurements, such as a beam's length in meters or a hole's diameter in inches. Floats are important because measured values often need decimal precision that whole numbers cannot provide. Strings are used to store text such as identifiers and descriptive names. For example, a pump identifier can be stored as text even if it looks like a number because it is meant for labeling rather than calculation. This helps distinguish text data from numeric or boolean values. This example uses booleans to track simple yes or no states. One value is true to show the inspection passed, while another is false to show the report is not ready. Booleans are commonly used this way to represent binary conditions in programming and engineering. The code prints each variable's value along with its data type to confirm it is being stored correctly. It checks an integer for a count, a float for a measured length, and a string for an identifier. This kind of output is useful for debugging and verifying that variables match their intended purpose. The total number of fasteners is found by adding the bolt count and sensor count using simple integer arithmetic. The result is then printed with a clear label so the total counted items can be checked and understood easily. This example shows how a string that looks like a number can still be used as a label. A pump identifier containing 12 is joined with the letter A to create the label 12A, which is then displayed as an extended pump label. The key idea is that strings can be combined to form meaningful identifiers, even when part of the string looks numeric. This line displays whether the inspection passed and confirms that the value is a Boolean. It uses Python's type checking to show the variable's data type by name, helping verify the inspection's logical status in an engineering workflow. Create a formatted message that combines the assembly name with the number of bolts used. An F string inserts these values directly into a readable sentence, which is then printed to summarize the assembly's bolt usage. This script shows how common data types represent engineering information. Integers store counts, floats store measurements, strings store identifiers, and booleans store true or false states, such as inspection results. It also demonstrates basic operations, including adding integer counts, extending a text label, and formatting a clear summary that combines text with a count. String values. In engineering, strings store text such as labels, descriptions, material names, component IDs, and status messages. They may contain digits, but they are not used for arithmetic. A numeric pressure value can be calculated with, while the same digits in a label only identify or describe something. Strings are sequences of characters that Python keeps exactly as written, so they are useful when wording and order matter. They often store labels such as sample names, testing conditions, part codes, machine names, file names, and user messages. By adding context to numbers, strings help make data easier to understand and interpret correctly. Be careful with values that look like numbers but are still stored as text. Text is joined as characters, while numbers are used for calculation, so confused numbers and text can cause subtle engineering errors. Use strings for labels and descriptions, and convert inputs to numbers before using them in calculations or simulations. Python code. String values. Strings are used to store text labels in engineering work. When text looks like a number, it must be converted before doing numeric calculations. Clear reports often combine text with numbers to present results effectively. The sensor is labeled with a text identifier, pump02 pressure sensor, so it can be clearly referenced in reports or logs. The measurement unit kPa is also stored as text, making it easy to display alongside pressure values for clear data presentation. Store both the pressure measurement and the maximum allowed pressure as floating point numbers. This supports precise calculations and reliable comparisons, which are needed for accurate engineering decisions. The number 248.6 is first stored as text so it can be combined with other text. It is then joined with the unit label kilopascals to create one clear string for reporting or display. Convert the pressure value from text into a floating point number so it can be used in calculations. Then, find the safety margin by subtracting the current pressure from the limit, showing how much room remains before reaching the maximum allowable pressure. The process checks that text labels and numeric values are stored in the right types before using them. Text values are confirmed as strings for clear labeling, while pressure values are confirmed as floats so calculations are accurate. The pressure reading is then combined with its unit for reporting, and the safety margin is calculated as the limit minus the converted pressure, formatted to one decimal place with the correct unit. This script shows how Python handles strings and numbers in an engineering-style calculation. It combines a numeric value stored as text with a unit label for reporting, then converts that text to a floating point number before doing math. After calculating a safety margin by subtracting the pressure from a limit, it displays the relevant data types, the descriptive text, and the margin with units. The main lesson is that type conversion is essential for accurate calculations and clear output. User input basics. Input prompt basics. Interactive programs ask users for needed information while they run, then pause until the user responds. This is useful in engineering because calculations often depend on changing conditions, such as a beam length or temperature. Clear prompts are important so users know exactly what input to provide. When a program asks for input, the prompt should clearly state what the user needs to enter, including the required units. This helps prevent mistakes, such as confusing meters with millimeters or entering the wrong cost basis. Clear prompts are especially important when other people use the program, because they should not need to inspect the code to understand the input requirements. User input is first received as text, even when it looks like a number, so it must be converted before calculations can use it. Clear input requests help users provide data in the expected format, such as entering only a number for a temperature or including a unit when required. Good instructions reduce errors and make conversion easier. Python code, input prompt basics. This example highlights the value of writing clear input prompts. Effective engineering prompts should include useful units, and mock responses can help keep Colab execution automatic. First, define a clear message asking the user to enter the beam length in meters. Stating the unit helps guide the user to provide input in the expected format, which supports accurate calculations later. The code simulates user input by storing the value 2.75 as text in a variable. This lets the program be tested as if a user had typed the response, without requiring actual interaction. The input starts as text, even though it represents a number. Converting it with the float function changes it into a decimal number, so it can be used in mathematical calculations. The beam length is converted from meters to millimeters by multiplying it by 1,000, since 1 meter contains 1,000 millimeters. The converted value is stored separately for use in applications that need millimeter measurements. The code displays the prompt text used to ask the user for input. This helps confirm what the user was asked and supports a clearer input process. The code prints the simulated user response to show that input is received as text, even when it looks like a number. This highlights why you must check and understand input data types before using them in operations. The code displays the data type of the typed response variable to show that the original input is still stored as text before any conversion. It uses the type function to identify the data type and then shows the type's name in the output. This helps illustrate how the script checks and handles data types. We check the data type of the beam length value to confirm it is stored as a floating point number. Printing the result verifies that the text was successfully converted into a numeric format, making it ready for later calculations. The code uses a formatted string to present the beam length clearly in both meters and millimeters. It shows meters to 2 decimal places and millimeters as a whole number, making the output precise, readable, and suitable for engineering use. This script shows how to turn user text input into a number for engineering calculations. It treats a beam length entered in meters as text, converts it to a floating point value, then converts the length to millimeters by multiplying by 1,000. It also displays the input and the data types before and after conversion, reinforcing why clear prompts and correct type conversion matter for accurate calculations. Converting numeric input. In an interactive session, entered data is first treated as text, even when it looks like a number. This matters because text cannot be used directly for calculations or comparisons. To work with values like measurements, sensor readings, or temperatures, the input must be converted into a numeric type. That conversion turns human-readable input into data the computer can actually compute with. Choose a numeric type based on what the input represents. Counts, such as specimens or bolts, should be integers, while precise measurements like diameter, voltage, or load are usually floating point values. Using the right type preserves the meaning of the data and helps avoid confusion in calculations, especially in engineering, where measurements often need decimal precision. Numeric input should be checked carefully before it is used in calculations, because unexpected entries such as blanks, words, units, or unusual decimal formats can cause conversion errors. A good script guides users toward a valid number format and treats conversion as an important checkpoint. This helps prevent mistakes and supports accurate results, especially when decisions affect design, records, costs, or safety. Python code, converting numeric input. Numeric input often starts as text, so it must be converted before it can be used at reliable engineering calculations. This example shows how interactive entries can be handled by converting them into the needed numeric form. Sample user responses are first stored as text. A length value of 2.75 meters and a bolt count of 8. This reflects how user input often arrives as strings, even when it represents numbers. These text values can later be converted into numeric types for calculations. Convert the length input from text to a decimal number, so calculations can handle precise values. Convert the bolt count to a whole number, because bolts are counted as discrete items. These type conversions ensure later calculations are accurate and meaningful. Convert the length from meters to centimeters by multiplying by 100. Then find the bolt spacing by dividing the total length in centimeters by the number of bolts, giving an even distribution along the length. The program first confirms that the original length value is stored as text, then shows the converted length as a floating point number, and the bolt count as an integer. It converts the length from meters to centimeters and prints it to one decimal place. Finally, it divides the centimeter length by the bolt count to estimate bolt spacing, formatting the result to 2 decimal places. This script shows how text inputs must be converted into numeric types before they can be used in calculations. A length is converted to a decimal number, and a bolt count is converted to a whole number. The program then changes the length from meters to centimeters, divides it by the number of bolts to find spacing, and prints the results with formatted decimal values. The main point is that correct type conversion is essential for accurate engineering calculations. Converting user input. In interactive Python programs, user input is always received as text, even when it looks numeric. To use it in calculations or comparisons, convert it to the appropriate number type, such as an integer for counts or a float for decimal measurements. This conversion lets user-friendly input work correctly in precise computations and prevents errors from treating numbers as text. When converting user input in engineering applications, choose the data type based on what the input represents, not just how it looks. Counts should become whole numbers, precise measurements should become decimals, and identifiers such as room numbers should stay as text. Matching the conversion to the input's purpose helps the program calculate, compare, and handle data correctly. When converting user input in Python, programs should expect messy data such as extra spaces, units, commas, or words instead of numbers. Good input handling guides users toward valid values and converts data consistently. This is especially important in engineering programs, where incorrect values can affect calculations like concrete volume or electrical load. Python code. Converting user input. Convert text input into numeric values before using it in engineering calculations. This allows user input to be handled safely and makes the results more reliable. We simulate user input by storing values as text strings. These include the number of bolts with extra spaces, the beam length as 2.75, and the load as 1250.5. Treating them as strings mimics real input, so they can later be converted into numbers for calculations. First, remove any leading or trailing spaces from the bolt count text using the strip method. Then convert the clean text into an integer with the int function, so only the numeric characters are processed and the conversion works reliably. The beam length and load values are cleaned by removing extra spaces, then converted from text into floating point numbers. This makes both inputs usable for precise engineering calculations involving decimal values and numerical operations. To find the load on each bolt, divide the total applied load by the number of bolts. This gives the load per bolt, helping engineers check that each bolt can safely carry its share and reduce the risk of structural failure. The output checks that the bolt count was correctly converted to an integer and the beam length to a floating point number. It then presents the total load, load per bolt, and beam length with appropriate decimal formatting. This makes the results easier to read while confirming that the conversions, calculations, and units are correct. This script shows how to convert text-based input into numbers for engineering calculations. It cleans the input text, converts values such as bolt count, beam length, and load into the right numeric types, and uses them to calculate the load per bolt. It then prints the converted types and formatted results, helping ensure calculations are reliable and outputs are easy to read. Formatting engineering results. Float formatting. Float formatting in Python controls how decimal numbers are displayed in outputs, such as reports or logs. It lets you show only the needed decimal places, making results easier to read without changing the underlying value. This is especially useful in engineering, where numbers must remain precise while avoiding distracting extra digits. In engineering, float formatting helps turn computational results into values people can interpret and use responsibly. Too many decimal places can imply false precision, while too few can hide important changes. Engineers choose the level of detail based on the context and industry expectations, so results remain clear, comparable, and useful for decisions. Float formatting makes numerical results easier to read, compare, and share. In engineering scripts, consistent formatting helps outputs appear predictably, which reduces confusion and supports clearer reports. Learning this skill helps students treat numerical output as an important part of effective engineering communication. Python code, float formatting. When preparing engineering reports, format floating point results so they are clear and appropriately precise. Use f-strings to control the number of decimal places and compare the raw calculation output with the formatted version to see how formatting improves readability. To calculate pipe velocity, use the flow rate of 0.0187 cubic meters per second and the pipe diameter of 0.1524 meters. First, find the pipe's cross-sectional area from the area of a circle, using half the diameter as the radius. The fluid velocity can then be determined from the flow rate and this area. The calculation first finds the fluid's average velocity by dividing the flow rate by the pipe's cross-sectional area, giving a result in meters per second. It also defines a constant pressure drop across the pipe in pascals and a small beam deflection measured in inches. These values are prepared for clearer presentation later. We display the raw results for velocity, pressure drop, and beam deflection before applying any rounding or formatting. This lets us inspect the direct outputs of the calculations and verify the initial values clearly. The calculated results are formatted with appropriate precision and units to make them clear for technical reporting. Velocity is shown to 2 decimal places in meters per second, pressure drop to 1 decimal place in pascals, and beam deflection to 3 decimal places in inches. This keeps the data professional, consistent, and easy to interpret. The output creates a neatly aligned design summary with columns for case, velocity, and pressure drop. It first prints a header, then shows case A using the calculated velocity to 2 decimal places and pressure drop to 1 decimal place. Case B uses the same formatting, but scales the velocity by 1.18 and the pressure drop by 1.35 to represent different design scenario. This script shows how Python F-strings can make engineering calculation results clearer and more professional. It computes values such as fluid velocity, pressure drop, and beam deflection, then formats them to appropriate decimal precision. It also aligns design alternatives in a readable summary so velocity and pressure drop can be compared easily. The main lesson is that careful formatting improves both accuracy presentation and readability in engineering reports. Decimal precision. In engineering, decimal precision should reflect the true accuracy of the data. Too many decimal places can imply unsupported accuracy, while too few can hide important detail. The goal is to format results so they match the measurement process, the audience's expectations, and the decisions that depend on them. Choose decimal precision based on the context and the consequences of rounding. Civil engineering measurements may only need 1 or 2 decimal places, while electronics often require finer precision because small changes matter. Environmental readings should match the sensor's actual resolution. Using the right number of decimals avoids false precision and supports better comparisons and decisions. Consistent decimal precision makes technical results easier to read, compare, and trust. It helps clients and engineers quickly spot meaningful differences in repeated values such as costs, performance measures, or pressure readings. The chosen precision should preserve the meaning of the calculation, avoiding both excessive rounding and unnecessary digits. Good formatting balances accuracy, clarity, and professional judgment. Python code. Decimal precision. Decimal precision is important in engineering communication because the number of displayed digits should reflect the confidence in a measurement. In Python, formatted strings can control how many decimal places are shown, helping results appear clear, consistent, and appropriately precise. The setup stores 3 engineering values with appropriate precision: a part length of 25.4 millimeters, an applied force of 1,234.56789 newtons, and an area of 78.539816 square millimeters. Together, these measurements provide consistent inputs for later calculations. Calculate stress in megapascals by dividing the force in newtons by the area in square millimeters, keeping the engineering units consistent. Then define the safety factor as the ratio of maximum stress to actual stress, and record the project cost in dollars as a floating point value. The code first prints the raw stress value as a baseline, then shows formatted engineering results to demonstrate controlled precision. It also displays the part length to 1 decimal place, matching the level of detail expected in engineering output. Report the applied force in newtons rounded to the nearest whole number, since extra precision is often unnecessary. Then show the area in square millimeters and the stress in megapascals, each rounded to 2 decimal places for clear, consistent engineering results. The code uses Python formatted strings to present results clearly and consistently. It shows the safety factor to 2 decimal places and formats the estimated cost with a $sign and 2 decimal places. This makes engineering and financial values easier to read and communicate. This script shows how to use Python f-strings to present engineering results with appropriate decimal precision. It calculates stress from force divided by area, then formats values such as length, force, area, stress, safety factor, and cost to practical numbers of decimal places. The goal is to make results clear, concise, and consistent with the confidence level of the measurements. Unsigned formatting. Unsigned formatting is useful when only the size of a value matters, not whether it is positive or negative. In engineering, signs can indicate direction or energy flow, but some comparisons focus only on magnitude. For example, when comparing a measured pressure with a reference, the important point may be how large the difference is, not which side of the reference it falls on. Unsigned formatting is useful when the key question is how large a deviation or demand is, not which direction it goes. Engineers may use absolute values for part deviations, foundation movement, or voltage changes, so they can compare results directly with tolerances, limits, or safety thresholds. This keeps attention on magnitude and supports practical pass or fail decisions. Unsigned formatting can make data easier to scan, but it can also hide important meaning when direction matters, such as gain versus loss or inflow versus outflow. Engineering reports should pair unsigned values with clear labels and descriptions so readers understand the context. The goal is to present data in a way that supports fast, accurate engineering decisions. Python code, unsigned formatting. Unsigned formatting is useful for presenting engineering results as clear magnitudes without implying a negative direction or sign. It helps keep values easy to read while still preserving their engineering meaning. For beginners, the goal is concise output that emphasizes the size of the result without unnecessary detail. Signed measurement errors show both the size and direction of deviations from a reference. Here, the pressure is 2.735 kilopascals below its reference. The hole size is 0.084 millimeters above its reference, and the position is 0.0126 inches below its reference. These values make it clear whether each measurement is too high or too low. Take the absolute value of each signed error to focus only on its size. This gives the magnitude of the pressure error in kilopascals, the hole error in millimeters, and the position error in inches, without considering direction. Using magnitudes makes it easier to compare how large the deviations are without positive or negative signs. The code displays 2 versions of the pressure error. The signed error shows whether the measurement is above or below the reference, while the unsigned error shows only the size of the difference. Both are formatted to 2 decimal places, making it easy to compare the error's direction and magnitude. The code reports the absolute size deviation of a hole in millimeters to 3 decimal places, then reports the absolute positioning error in inches to 4 decimal places. Both values are shown without direction, focusing only on the size of each deviation. The code determines whether the tool is below or above its target position by checking the sign of the position error. A negative error means the tool is below target, while any other value is reported as above target. It then prints this diagnostic note to help identify the direction of the positioning error. This script shows how signed measurement errors can be converted into absolute magnitudes to make engineering results easier to read. It compares signed and unsigned pressure error then reports unsigned hole size and position errors with appropriate precision. It also keeps important direction information by noting whether the tool position is below or above the target, supporting clear diagnostics without cluttering the output. In this lecture, you learn to distinguish between strings, integers, floats, and booleans in engineering calculation contexts. Build interactive scripts that accept user input and convert it to usable numeric values. And format calculation results clearly for engineering interpretation and reporting. In the next module, Module 2, we will go over control and functions. Thank you for your attention. See you all in the next lecture.